Good morning or good afternoon, depending on where you're at. My name is Atarot Azizi Namini, Director of the IBT/ABC UTC. Very warm welcome to our quarterly research seminar. I just wanted, before we start, just to share some very exciting news at this point. Now we have upcoming 2026 World Bridge Engineering Conference that's going to be emphasizing innovative bridge technology and ABC to be held December 1st and 2nd. 2026, which is sponsored by USDOT. Now we have more than 30 states that they have co-sponsored. So at this point, I'm going to turn it to Frey. Take it from here.
Welcome to today's IBT ABC UTC Quarterly Research Seminar. The presentations in these seminars highlight research work at the IBT ABC UTC's partnered universities. Each seminar consists of a 40-minute presentation followed by a 15-minute question and answer session. My name is Frey Pozo, and I'm a research assistant professor at the IBT ABC UTC. I'll be moderating today's seminar, and I'm assisted by Don Digamon, Georgia State Bridge Engineer, and Paul Lies, the former Georgia State Bridge Engineer. Don and Paul will be moderating the Q&A session. Before I introduce our presenters, I will review some housekeeping items. Many of you may know these research seminars are recorded and posted on the IBT ABC UTC website in the section titled Research Seminar Archives. So you can access this and all previous seminars for future learning and to share with your interest colleagues. I would also like to point out that a PDF version of today's presentation is provided in the GoTo dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. Lastly, this presentation will be followed by approximately 15 minutes of questions and answers. The seminar today presents IBT ABC UTC research project on Transformative Bridge Asset Management using an Integrated Graph Network-RNN, or Recurrent Neural Network approach, that was conducted by our partners at the University of Georgia. We are pleased to introduce our presenters, Adeyemi Sowemimo, a PhD candidate at the University of Georgia, who will introduce the other presenters.
Good afternoon, everyone. And thank you so much for the introduction, Frey. Today, excited to present our work on transformative bridge asset management using an integrated graph network and RNN approach. And well, this project is one of the funded UTC project, the University Transportation Center project, handled by the University of Georgia, under the guidance of the UTC co-director, Dr. Bjorn Bergersen, who is also the chair of the School of Environmental, Civil, Agricultural, and Mechanical Engineering at the University of Georgia. For this presentation, it's going to be in three major phases. For the first part of the presentation, Dr. Micho Zepa is going to explain the major elements of the next generation bridge asset management system. And then for the second part, I'm going to go over the temporal modeling component using the recurrent neural networks. While for the final part of this presentation, Dr. Sajib Saha will cover the graph network framework, which captures the connectivity and spatial relationships across the bridge network. So I'm going to hand over to Dr. Chozepa to go over the bridge asset management system.
Thank you, Adi. My name is Micho Zepa, faculty at University of Georgia. We're working on the next generation bridge asset management system. As you all know, FIU is the lead institution, collaborating with other partnering university and us. And the core element of asset management I have identified so far, working with other university, not limited by the elements here, are rehabilitation and retrofit, and elements supporting service life predictions and real-time response and data, and also inspection, assessment, automation, twin technologies, UAV, and connected smart infrastructure. And another element that are identified as important is framework to embrace innovation and change. You heard about 3D printing, advanced materials, additive manufacturing, disruptive technologies, and some of these elements, also decision-making assistant through AI and scenario analysis, and even being able to see these in the metaverse space was identified as important. So with that said, any state DOTs interested in becoming the member of EDA committee, which is created by Dr. Atrat Azizinamini, is invited to join the development effort. And Don Digman with the Georgia Department of Transportation will be chairing this committee. And to support bridge asset management at UGA, we have quite a bit of students working on research on asset management. And the first student, we actually made a video to share with you and with photos, but we're not able to play. So I'm just going to briefly go over some of these highlights. I'm sorry, their face is not able to be shown here. And Ozzy is working on wireless sensors and bridge monitoring with Georgia DOT. And Ibra is doing adaptive learning and cross-referencing distress with advanced nonlinear finite element modeling. And Mohammed is working on looking at bridge district data and how they interact with MBI deck rating. And Mason is working on type 1L HE cement to replace type 3 cement and mixing concrete mixtures at the lab. And Jace and Sarah is working on developing in-person, on-demand bridge training modules for off-system bridge owners. And this is ongoing effort, and we'll be able to deliver the first training module with a district shortly. And Sachin is another student, PhD student, working on delivering and enhancing bridge education. And this was for knowledge transfer. And this project particularly is funded by PCI Foundation, Georgia Carolinas PCI, and in conjunction with resources provided through FIU, we are teaching our students delivering hands-on experience in fabricating precast bridge elements. And another element of knowledge transfer at UGA that we're working on as a part of the UTC member partner is we have just launched online masters in civil engineering, and we are requiring bridge engineering studio as part of this class, and we collaborate with Georgia DOT, Don Digman, and Ravendra with maintenance and more, and also design companies such as MBI, Gresham Smith, and hoping to collaborate with them more, and also show the fabrication process with the standard concrete products, also highlighted construction with the CW Matthews, and finally, we are teaching the concept of accelerated bridge construction with the FIU, FHWA, State DOT resources. Thank you. With that, Audie, it's all yours.
Okay, thank you, Dr. Chiazepa. Well, I'm also one of the students, just like some of the slides you showed earlier, but I've been given the opportunity to talk more about my project. So to give an overview of this presentation we have here today, this project is going to introduce a framework that combines the recurrent neural network and the graph network to model bridge performance both temporally and spatially. In this project, the RNN is going to capture how bridge condition is going to change over time, while the graph network is going to model the spatial relationship across the transportation system. And combining both of them, they are both going to support a proactive maintenance and network level decision-making process. And it gives DOTs a powerful tool to assess infrastructure health across time and space. For this project, I'm working majorly on the service life prediction part of the next generation bridge asset management system. So now I'm going to go over the development and the performance of the RNN models. But before I go into the development of the RNN prediction models, I'll quickly go over the two metrics that we're going to be predicting. In this case, two metrics that are used to assess the condition of a deck. The first one is the deck condition rating. And this is a rating on a scale of 0 to 9, used to assess the physical state of a bridge deck, usually based on visual inspection by bridge inspectors. And the deck condition rating can range from a range of condition rating 9 to 7, that is when the deck is in almost a perfect state. And then it can also range from condition 6 to 5, wear and tear has occurred on the deck, so it's in a satisfactory to a fair condition. And then the last set of conditions are from condition state 4 down to a 0, where the deck is in a poor condition or a failed condition. And in most cases, the bridges are always closed. And for this kind of terms of developing a deep learning model, the deck condition rating is a classification task, mainly because we're choosing from a fixed range of labels, that is from a range of 0 to 9. These are like fixed labels. So it's not like predicting a continuous number. While the other metric in this case, which is the deck health index, is we're trying to predict continuous value, in this case from a range of a 0 to 100. And the deck health index is a composite score that quantifies the overall condition of the bridge deck by considering the extent and severity of a defect across the deck area. In this case, this tax is a regression tax for the models we're going to develop. And briefly, I'm going to go over some of the prediction models out there. As we all know, we have so many prediction models out there, but my major focus for this presentation is going to be on the models present in the FHWA InfoBridge platform. The platform contains 3 major predictive models for the bridge components. And what I mean by components are the deck, the superstructure, and the substructure. The first of this model is the base model, which is a statistical deterministic model, while the second model was a survival model, and then finally they have the machine learning model. Now, going over the first model, which is the base model. The base model generally uses the historical time in condition data for similar bridges to predict future conditions. And what I mean by this is it looks at bridges with similar features and learns how their conditions have changed over time. From this plot, you can see the blue line shows the actual past condition rating for this selected bridge. And then these green dots right in front of it are the model's predictions based on how similar bridges have deteriorated in the past. The second model present in the FHWA InfoBridge platform is the survival model. And it works by using a combination of survival analysis and Markov chains. And it does this by calculating the transition probability of changing from one condition state to another over time. But for the 2 models I've gone over so far, one major limitation with both of them is they majorly focus their prediction based on the past condition state and ignore factors that can influence the change of bridge condition over time, such as traffic, the bridge age, the bridge material, and the likes. But one FHWA model that actually incorporates all of this is the machine learning model, where they made use of the convolutional neural network, the CNN. And in this case, the CNN learns the patterns from the bridge features to predict how bridges deteriorate over time. At the University of Georgia, one thing we developed is a model that also considers all the features just like the FHWA CNN model. But one thing we added to it was to have a model that captures temporal progression and also has an improved accuracy. So we developed the recurrent neural network model, in this case, the LSTM, that is the long short-term memory model, and the gated recurrent unit model, which were both designed to process the input data year by year. And what I mean by this is, let's say we have 9 years of bridge data. The model is going to learn how the bridge condition has evolved from the first year down to the 9th year. And then it's going to use the learned sequence to make predictions of what is going to happen next. So RNN, in summary, generally learns when and why deterioration happens and not just make predictions of what's going to happen next. In the development of prediction models, there are several steps involved. And the first step is to retrieve the necessary database we need to build the model. So we collected 9 years of the National Bridge Inventory data and bridge element data. And this database generally contains the relevant geometric and operational features needed to process the development of the model. And in training our models, we wanted to build a robust model that's going to generalize well. So we needed to select 2 states with contrasting bridge deck data. So we carried out a nationwide deck assessment using the 2024 National Bridge Inventory database to determine the states with the highest percentage of decks in good and poor condition. So first we looked at the percentage of decks in good condition. And you can see from these figures, the states with the darker shades of green, just like Texas, Florida, Georgia, they indicate the states that have a high percentage of decks in good condition. And so from this, we were able to select Georgia as it ranked #1 in the country. And then on the other side of this, we looked at the percentage of decks in poor condition nationwide. And we narrowed this down to Iowa and Maine as one of the top 2 states with a high percentage of decks in poor condition. And but we decided to go with Iowa as they have more number of bridges than in Maine. In Iowa, they have more than 20,000 bridges, and in Maine, they have less than 3,000 bridges. And one thing about training a deep learning model is the more data points you have present, the better it is for the model to learn. And since the assessment we carried out so far was done using just 1 year data, the 2024 MBI data, we decided to look at the trend for the selected states. And in this case, we selected Georgia for the states with a good high percentage of decks in good condition, and Iowa for the other side of it. And so one thing we did was to look at the deck condition rating for the last 5 years to better understand the trend in each of the states. And one thing we noticed was that in Georgia, there's an upward trend in the percentage of decks in good condition, while in Iowa, the reverse is the case. And having this kind of contrast is very good for training our prediction model, because it's going to be very robust. But for the rest of this presentation, my major focus is going to be on a model we trained using the Georgia database. And so for the Georgia data, we're able to select a set of features that were used to train the model in predicting each of the metric we wanted to predict. And in the first case, we want to predict the deck condition rating. We had this set of features selected. And then for the deck health index, we had this set of features selected. And we came about these features from several iterations, relating with several literatures, and also from the conversation we had with some DOT personnel. But one thing to mention is for other states that plan on implementing this approach, the set of features that will be selected for each state, it might differ. So this is generally just for the state of Georgia. So if you want to try this for your state, the features that are going to be used to make predictions for your condition rating or your deck health index is going to be different. So the next thing we did was to arrange the data in a sequential manner. And what I mean by this is to get the data. We collected data from 2016 down to 2024. So this is a sample of how the data is going to look like for a sample bridge. So you arrange the data from 2016 down to 2024. Then you have the target variable, which in this case is the deck condition rating, what we're trying to predict, and you line up each of the features that you selected for predicting this target variable. But one thing we're going to notice looking at all these features is they all have different range of values. And for a model to learn properly, you have to keep the values in a similar range. So we normalize the data to a range of 0 to 1 using the mean max normalization. And once we normalize each of the features, we add the data in this format. So the next thing we did was to frame it into a supervised learning format. And what I mean by this is we had to put it into an input and output pair, but still maintaining the sequential nature of the bridge data. In this case, the lag features they served as the input for the target variable. And in this case, the target variable is either the deck condition rating or the deck health index. After this, we had to restructure our input data in a 3D format. And what I mean by 3D is have it in a sample, time step, and feature format. And sample in this case means the bridge IDs, which is the first dimension. The time step is the number of years, which is the second dimension. And the third dimension is the features, which is the number of features used to make predictions. After this, we carried out a data split on the main data set to use 70% of the data for training, 15% for validation during training, and 15% for testing after training the model. So once we have our input data in a 3D format, we then feed it into stacked layers of RNNs. And in this case, we made use of the long short-term memory model, which is the LSTM, and also the gated recurrent unit model, which is the GRU. And we selected both models because they are generally ideal for this kind of tasks, because they are designed to capture temporal dependencies, and also they retain memory across long time spans, unlike the regular feed-forward models. What I mean by all of this is, for example, a rehabilitation in a particular year could influence the condition trend for that selected bridge several years later. These selected models, the LSTM and GRU, are capable of learning that relationship and what causes this change in condition trend. And one thing we did during the training of the model to prevent overfitting was to include a 30% dropout after each of the RNN layer, before then feeding it into the final dense layer for transformation. Then we move then going into the output processing layer. For the deck condition rating, we made use of the softmax activation function to predict a probability distribution across the deck classes for each year. And while for the deck health index, we made use of the hyperbolic tangential function. And then we got our prediction in a 2D format, which is the bridge IDs and the set years of predictions. Just to hammer on this, one of our recent works we've completed was modifying this architecture to improve it even further better. One thing we did was to replace the dense layer, which I just mentioned, with a time distributed layer, as the dense layer would typically flatten the entire sequence into a single vector. So the data is going to lose its time structure and kind of weaken the model's ability to recognize year-to-year changes. While the time distributed layer, which we included, was very good for the model because it helps the model to preserve the order of time steps and allow the model make a prediction for each year. And including this time distributed layer moved the whole model from a many-to-one to a many-to-many forecasting framework. And this is very important for bridge condition predictions, where timing and sequence actually matters. Now, looking at the overall performance of the models we've trained, for the regression model, which is the deck health index, which is a regression tax, where we have to predict a continuous value between 0 to 100, see that both the LSTM and the GRU models achieve the high accuracy with a high R-square value above 0.9. And if you look on the right, we have a plot for a sample bridge that compares the predicted values to the actual deck health index over time. On the y-axis, we have the deck health index that ranges from 0 to 100, while on the x-axis, we have the years which we tested with, that is from 2016 to 2024. And in this plot, you can see the blue line, which represents the actual deck health index, while the red and green lines just shows the LSTM and the GRU prediction. And we can notice by looking at this that both models actually track the real world deterioration. And between 2017 and 2018, where there's a massive drop in the deck health index for the selected bridge, and also between 2021 and 2022, where there's an improvement. So this is just not a deterioration model. It also captures appreciation in bridges. And then on the other hand, we looked at the performance of the models for predicting the deck condition rating, which is a classification tax. And we can see that both models shows a strong overall performance with an accuracy of about 87%. But with Georgia bridges, since the data is a bit imbalanced, and what I mean by imbalanced is most of the deck condition rating are clustered around condition rating 6 to 8. So accuracy alone is not going to tell the a full story of how the model performed. So we dug deeper, the class-wise analysis. And so with a bar chart on the right, we can see a breakdown of the performance of each of these models in a class-wise manner. And we can see that the LSTM, which is the one on the top right, does a better job at capturing the rare classes, which is class 0, class 3, and class 4, when compared to the GRU model. And then we selected a sample bridge to test how both models actually track real inspection over time. And looking at this plot, we can see that the LSTM prediction closely tracks the real world data. And now to evaluate the long-term use of the trained model, we selected the best performing classification model to make a future bridge deck condition rating predictions from 2025 to 2032. And using the model learns from historical data from the state inventory to make good predictions. And we can see that the model predicts a minor deterioration in 2025 and then reverts to the longer term stable trend it has observed in the state inventory. But since Georgia bridges exhibit mainly an improving deck condition trend, evaluating the RNN model, the RNN model ability to actually predict progressive deterioration could not be adequately tested using Georgia data alone. So to fairly evaluate the model's ability to predict declining condition scenarios, we considered the data from the Iowa database we collected earlier. And using the same architecture but different set of features, we trained the model on Iowa data. And we selected a bridge in Iowa to make our future predictions also with the selected bridge. And from this plot, we can see that after a long stable period in condition 8, the actual rating drops to condition state 7 in 2024. And then the model picks up on this change, then predicts a slight recovery, and then a gradual decline in 2032 to condition state 6. And this behavior just reflects the Iowa training data set, which contains a lot of bridges in fair condition. And doing this, using another state data to test how the model is going to perform shows the importance of training the model for specific static regions, as it's going to capture the localized degradation behavior in each of these regions. And in terms of other application of this model, we extended the application in predicting the overall bridge health index, which combines the deck, the superstructure, and the substructure condition ratings using weighted coefficients. And we can see that both models, from this selected bridge, we can see that both models actually tracks the actual bridge health index value closely. And this just demonstrates the model's flexibility to be able to predict composite indices like the bridge health index and not just individual bridge components. And you can scan this QR code to get more information about this approach, because we recently published a paper that details a lot of the process in developing a model to make an overall bridge health index prediction. And then in terms of network performance, the 3D plot shown here shows the model's ability to handle multi-bridge forecasting effectively. And by doing this, we can allow DOT assess the condition of an entire bridge inventory simultaneously. And it also provides a clear view of the future trend of the bridges in an inventory, thereby aiding bridge owners in understanding the long-term health of bridge assets. And from a planning and budget allocation point of view, the ability to predict the future condition trend at both the bridge and network level helps in making data-driven maintenance decisions, resource allocation, and also long-term capital investment strategies. So in summary, with all what I've said so far, one thing I just want to hammer on is we have developed two prediction models, one with a dense layer and also one with a time-distributed layer, and both of them are capable of making bridge condition predictions. So that concludes my part of the presentation. I'm going to hand over to Dr. Sajib Saha now to go over the graph network part of this presentation.
Good afternoon, everybody. My name is Sajib Saha, and I work at University of Georgia as a research scientist. So in this UTC project, I have specifically worked on the scenario-based decision support part to develop a next generation of asset management system. So as already explained, in addition to the temporal prediction of structural condition rating, we utilized a graph-based modeling approach for spatial network integrity assessment. So as you know, highway system is inherently structured as planar networks. They can naturally be adapted to primal graphs. In doing so, we first acquired statewide roadway network dataset for Georgia in a geospatial format from Georgia DOT website. As you can see in the figure at the left, the Georgia network is consisted of 205,292 roadway sections. To obtain the spatial distribution of bridges in Georgia, a bridge geodatabase is also collected from the Federal Highway Administration website. Deck condition rating of those bridges, which is obtained from the National Bridge Inventory database, typically ranges from 0 to 9. But for Georgia, the rating is highly concentrated in between 5 to 8, as you can see from the figure at right. Now, to generate a graph network for the highway bridge system within Georgia's National Highway Freight Network, first of all, GIS shapefiles of the freight network have been collected from the Federal Highway Administration portal, as you can see from the figure at the left. So Georgia's National Highway Freight Network spans 1,753 miles and is comprised of the most critical highway segments connecting major cities such as Atlanta, Savannah, Augusta, Macon, and Columbus. And in the figure at the right, you can see out of total 15,505 bridges in Georgia, only 684 bridges are identified passing through this National Highway Freight Network. Now, once we obtain the shapefile of the National Highway Freight Network, a Python library Network-X is used to convert it into a network graph, as you can see in the figure at the left. This figure illustrates the structure of the network by displaying the distribution of node degrees. Here, the node means the intersection in the highway network, and the node's degree means the number of edges or pavement sections connected to it or connected to the intersection. The blue, green, orange, and red colored nodes here represent nodes with degrees of 1, 2, 3, and 4 respectively. The figure at the right shows the number of nodes in the network for each specific degree. Now, bridges within this highway freight network are integrated with the graph network of highways based on their geospatial coordinates. It is assumed in this analysis that bridges are the only component that can fail, which leads to the removal of an edge from the graph due to bridge closures. Now, here we can see various matrices which have been introduced in the past to assess the topological integrity and robustness of roadway network. Some of them are listed here, such as global efficiency, average distance, percolation limit, average node connectivity, maximum betweenness centrality, and network robustness index. So out of all these measures, we have seen the node connectivity, betweenness centrality, and robustness index are the most popular matrices. For example, robustness index matrix is characterized based on the average size of the giant connected component of a network after removing each node one by one. A description of what giant connected component is. So for our analysis, we used a metric named connectivity to assess the topological integrity. Now, connectivity is defined as the ratio of the size of the giant connected component after vulnerable nodes are removed and the original size of the network. So as you can see from this equation here. To illustrate it better, you can see the figure at the left. So the figure at the left demonstrates if the original intact network is comprised of 32 nodes and 33 functional edges, and 5 edges become dysfunctional due to a disruption, the network will break into 5 separate subnetworks. In that scenario, the largest subcomponent, which is the middle one in this case, will contain 18 nodes. Hence, the relative size of the giant connected component, or in other words, the connectivity under this disruption can be calculated as 18 over 32. Now, deck condition rating is selected as the performance indicator here due to high susceptibility of bridge decks to deterioration. A maintenance threshold value of deck condition rating 6 is assumed in this analysis to demonstrate the application of the graph-based network analysis. But we want to emphasize here that this assumption that a threshold value of deck condition rating 6 is just for an illustration purpose. Because of high deck condition rating across Georgia, lower threshold values such as deck condition rating 4 or 5 could not be meaningfully applied here. So in 2024, 68 bridges in the National Highway Freight Network are identified with a deck condition rating of 6 or below, as you can see in the figure at the left. Similarly, projection from the recurrent neural network model estimate this number, which is the deck condition rating of 6 or below, will decrease to 23 by 2032. Which also indicate improvement resulting from ongoing maintenance and repair activities across Georgia bridges. Now, these low-rated bridges are used next in the graph network analysis to show the potential impact of bridge closures on the freight network. So these illustrate the connectivity profile of the National Highway Freight Network for 2024. So this figure shows the change in the connectivity of the network due to randomly eliminating a certain percentage of bridges involving low deck condition rating. The process simulates the potential effect on the freight network due to bridge closures for repair or maintenance. So in order to reduce the possible impact of random sampling, 50 simulations are conducted in this analysis at each steps, with bridge removals occurring in 2% increments. So as you can see the figure at the right, 2% increment of bridge closure is conducted at each steps, and 50 random simulations are conducted to calculate the standard deviation and the mean value here. Similarly, the connectivity profile of the highway freight network for the year 2032 are depicted in this slide. Next, this figure compares the network connectivity between 2024 and 2032. The highway network in 2032, which is shown by this orange color plot, exhibit improved connectivity compared to the 2024 network, which is shown by this blue color plot, which also indicate greater resilience in 2032 for bridge closure, which involves low deck condition rating compared to 2024. To illustrate it better, for example, when 40% of the low-rated bridges are closed, the connectivity of the 2032 freight network is reduced to 65% of its original size, whereas in 2024, the connectivity drops to approximately 46%. Now, based on the results of integrated RNN model and graph network analysis, highly critical bridges are selected based on two independent factors. First one is low deck condition rating, and the second one, high network connectivity. The table here lists the network connectivity measures after the removal of each critical bridges separately. It also includes the current year 2024 and the future year 2032 deck condition ratings. The figure at the left illustrates the spatial location of those bridges in the network, highlighted in brown. Now, to assess the improvement after prioritizing repairs of those selected 6 bridges, we conducted a simulation study that reflects the state of network in 2032. The analysis focused on the 17 remaining bridges within the National Highway Freight Network that are predicted to have a low deck condition rating. The results indicate that the 2032 network, after repairing the 6 most critical bridges, as you have seen in the previous slide, exhibits significantly improved connectivity, as you can see the green plot, compared to before prioritizing repair actions, which is shown by the orange plot. It also indicates enhanced resilience to bridge closure after taking these repair actions for those selected 6 bridges. It highlights the value of integrating predictive condition assessment with topological network-based criticality analysis for prioritizing maintenance action and also allocate budget resources. Now, finally, I would like to discuss the practical application of our work for future investigation. So this integrated approach can be potentially applied to identify high-risk bridges within road networks under various disruptions, such as flooding or the introduction of automated vehicles. For the state of Georgia, the Interstate Intelligent Transportation System and the Connected Vehicle Implementation Project proposes to implement future connected autonomous vehicle system along I-75 as well as I-475 and 575, as you can see in the figure at the left. Now, 178 bridges in that project corridor will be exposed to heavy truck loads, which also increase the risk to potential disruption. Similarly, this flood hazard map and flood frequency class distribution map of Georgia illustrate the bridge closure probabilities at different flood zones. The network modeling approach can be applied to assess the impact of flooding events on road network connectivity and can also provide valuable insights for guiding bridge asset management decisions during this type of flooding events. Finally, in conclusion, this integrated graph network RNN modeling approach helps us to effectively identify bridges that pose a high risk to freight network connectivity and also support the prioritization of repair actions. This work can be further extended to other states' bridge network, can be tested on a larger, more diverse data sets as well for broader use in bridge asset management system. So that's the end of my part of the presentation. I would hand over to Dr. Georgieva to discuss more about the next generation of asset management system.
Thank you, Dr. Saha. This is a brief recap of next generation bridge asset management system. FIU is a lead institution collaborating with the UGA and other partnering university. There are core elements that we have identified. And one of the important elements, particularly service life prediction, we're still using past data and how do we use real-time data and sensors. And another thing is using evolving technology, twin, digital twin, and remote sensing, and even connected infrastructure. And in terms of replacement, There are a lot of things like project bundling and demand forecasting scenario-based that Dr. Sa kind of looked into, in smart contracting, and even some of these being able to look at inspection and replacement in the metaverse space. And Dr. Etrat Azizin-Amini has a internal white paper, and I've been meeting with him a couple of times to discuss what would be the element of next generation asset management. And he created ad hoc committee graciously chaired by Don Digman with Georgia Department of Transportation. And we are recruiting any state DOTs interested in becoming the member of ad hoc committee for the next generation bridge asset management. Please email Dr. Etrat Azizinami at the address shown on the slide. And that concludes our presentation. And if you have any question, please contact Bjorn Bergersen. He's the UGA, the director, UTC co-director, UGA PI. And with that, now, Kathy, we are ready for questions. Thank you for your attention.
Thanks to today's presenter for your interesting and informative presentation. Don and Paul will moderate the Q&A session. Paul?
We'll go on into the questions. We do have a few questions. We had one that came in beforehand. I'll ask that one first. And then we do have a few others that have come in. First thing here, and this came in beforehand, was our structural work recommendations tailored to the bridge elements and their respected deteriorated condition that you're predicting in the future?
It's not specifically, but that could be, as we said, that could be one of the parameter. If you were to train it with particular parameter, it could be part of the decision making. And if we can train it, and then another thing is with the result will look, the predictions or the performance will be great with a particular variable. So I think the short answer is yes. Any parameter could be a variable, and each state DOT would have different parameters. But we'll be happy to try. If that question is specifically from state DOT, we tried Iowa. We'll be happy to select another DOT and try. Feel free to contact us.
Okay. And I was curious on the data. You have it where you make the prediction starting at the last piece of data you have. Did you try going back and just say, I only have maybe 5 years back and I only have the data up to that point, and see what kind of a prediction it would make? Because you would know what it should make if you're looking at the data that you have for the 5 years. In other words, you chopped it off 5 years ago and said, hey, let's see what it says. And I just was wondering how accurate it was.
Initially, when we started testing the model with 9 years of data, that was the first approach. We saw how good it performed. Then we also tried with a shorter duration to see. The performance was also good, but not as good as when you have longer time data to train the model with, because it's going to learn more from a longer duration.
Yeah. All right, here's a bunch of questions here that we have. And the first one, it says, can you elaborate how the service life design would be incorporated into the next generation of asset management system? In other words, whenever we design a bridge, we have a service life that we're predicting. I don't know if that's put into anywhere, worked into the data.
Yes, and if you look at the core elements, service life prediction was a key element. And just like I highlighted, I would love to see the real-time data. We're still using past data, and Dr. Azizinami, I had this discussion, and if we have a lot of wireless sensors and a lot of real-time feedback and not using the past data. So short answer is yes. We would hope to, but we would love other state DOT users' feedback, and that's why we're inviting you to join the ADA committee to provide us feedback and their recommendations.
That's good. Then there's a question here. We've had some things where we do bridge bundling, where you work up a whole bunch of bridges in a contract. And I don't know if there's any way to incorporate bridge bundling into the new asset management system.
Absolutely. I think that will be the key element of next generation asset management system, because all the budgeting will be done in bundling. I think that will be a very important part of the next generation bridge asset management because of the economy of the scale and doing it in bundling. So that would love Georgia DOT and other DOT's feedback in expanding that asset management system work. So absolutely.
Okay. We have a question here. It says, are you simply using FHWA the info bridge, or are you using the data and creating your own platform when you're doing the program?
Not really. I think FHWA has a platform, has a great prediction models, but we also have UTC-funded research project. So we wanted to push beyond what's available. It does have a great machine learning model that we like, and it has a pretty good accuracy. But since we are researchers, we wanted to push beyond and have that time prediction element. And it did improve accuracy quite a bit, and because it actually remembers all the sequence of each bridge. So the time distributed layer in our model actually remembers the sequence of each bridge. It's not just try to bundle all the bridge behavior. It's very bridge specific, if you will. So yes, FHWA model definitely, and we're not trying to create new dashboard though. We're just trying to enhance the scientific prediction model beyond what's available. But we really like FHWA InfoBridge website, and that's where our starting point was. We read all the literatures used to predict that prediction, and we loved it, and that was kind of Audie's starting point.
That's good. We have a question here, and I may elaborate on it some. It says, bridges that we design now use different technologies. How does that affect the use of the old performance data?
So that's one of the ideas. So we wanted a framework that can incorporate evolving technologies. So I would have to be honest, and I don't have immediate answer for that. For next generation bridge asset management, I would like to have a clear answer for that. So as these technologies develop, I strongly believe next generation asset management should be able to evolve with it, not one of those closed one-time application that does one function, and then next time you're doing it, you have to invent the whole system, if you will.
It's real good. We've had a number of presentations using precast elements everywhere. And then we have a number of presentations using ABC technology. And that may not be reflected in your long-term data, just at the end. So we were just wondering how all that would fit in. Okay.
That actually give us a good idea of maybe doing prediction on ABC bridges only. Audie?
That's a good one.
Yeah, that's actually give us a great next research.
That would be a good one. Yeah, we'd be real interested in that. And everything we've seen is they're performing real well, but it's just it's always good to see data. So anyway, let's see. In assessing the condition and future performance of bridge deck use with a single index is used in the NBI, National Bridge Inventory, that may not be enough. How would you address that issue?
So that kind of reminds me of one of the projects that we're working on. We're looking at districts data. So if we look at NBI rating as a one value, and let's say inspectors went out to look at the bridge deck 3 days after the district has repaired the deck, or had to patch the spalling, and the rating, we look at the rating, it's good. So the rating that we see in National Bridge Inventory, it would be nice to have the mechanism to feed into how much money we spent. And it goes back to kind of the next generation asset management system framework. We want to be able to see return on investment, optimizing return on investment. So not in addition to NBI data, if we can leverage evolving data with agencies, and we can potentially better inform the decisions and look at ROI, return on investment, kind of for that specific bridge. And with the Dr. Saad's work, we can look at it network-wise and just not just MBI. So you're right at the point of what we're trying to make through this presentation. The MBI alone, one, it's past data. Two, it's a one data point collected every other year. So if there's any way we can strengthen that data with evolving data available already and potentially with the real data collection that we can secure from the site, it'd be wonderful.
Okay, here's the question that came in on one of the slides. It was slide 17. The person noticed the predictions were less accurate for the year 2024.
Just to give you an idea, so Audie came with plots that had exactly identical. And he had a lot of those because the predictions, like R squared is 0.9 above. So I told him, please find the one that can show the difference. So he had a hard time finding one for the presentation. And Audie, you can answer why it goes up though. That's a great question.
The upward movement just shows predicted improvements, like a repair, a rehabilitation at that point for the bridge there.
And it probably comes from the fact that this bridge had some of the received the funding, had some increases. It remembers kind of the pattern at some point that condition rate is increased, then maybe there was action by the bridge owner, and then it tried to pick up. And I think that was one of the models that shows the difference the best. But we really had a hard time selecting one for presentation because they're really, with the 0.9 R square, it's identical pretty much.
Okay. Someone asked if the code used in the modeling available.
We could make it available. We would have to run it by Dr. Atrad as Zinamini. It's a Python script, and we'll be happy to share, and we'll be happy to show you if you're with this particular state DOT, we'll be happy to show you how you might train your data with it. And because there are multiple variables, and in Iowa, there might be different variable that might be more important. And what we try to do in this analysis, we kind of guessed what variable might work. But I think if you're with a particular state DOT, you probably know what might be a driving variable. So absolutely, we'll definitely ask that question to the director, UTC director.
Okay. How do you protect the model from inspector bias?
That's a good question, right? As of now, that's built into the model. Because the model we're training with data that already has inspector bias. But as I said, that could be also training variable. And you can train it with what type of variance you expect in inspection. And we've been looking at inspector names and see if there's a same pattern. And one of the things that Ari did was kind of, you can actually scan the inspection report and auto-identify text recognition. And you can see if the same inspectors using kind of same language and same way of rating. So short answer is yes, you can train it with inspection bias being as a variable. If you think that might work, and we wouldn't know until we actually try it.
Okay, this is an interesting question here. Can your model optimize across varying funding resources and percentages contributing to projects? Where there are various risks associated with those funding resources and models across optimum spending plans across 3, 5, 10, 15, and 20-year project database, depending on project risk or size. That's a pretty complicated question.
I love the question. This question is right on the money, and would love to be able to do that. One variable we would need is annual funding level and the number of bridges we might have had. So if we have a good database documenting the funding level, because the condition data already reflects the funding level. So if we can have that funding level as a variable and training, given that in terms of long-term prediction, if we have that long-term documentation with a varying budget level, absolutely we can make that a variable. But it's really driven by data. So just got to make sure data is accurate and we have the right variables and documentation to support it. So absolutely love the question and would love to be able to do that.
Okay, it's getting on to about 10 after. I'm going to go ahead and let Don come in. And Don, there's a few questions left.
Thanks, Paul, and good morning and afternoon to everybody. And again, just want to say this, and I'll say this probably later. Thanks for the UGA team on this really interesting work that you're doing. So the next question here, another good one. Could your model recommend road and bridge closures based on insufficient funding?
It should work for everything as long as we have database, so we can just run that for those specific bridges, whichever has the insufficient funding.
Yeah, I
So
can see that. We can use that for variable as a prediction. We use that prediction data in your graph network. So
yeah,
absolutely, give us data, we'll do it for you.
yeah, that's a good idea actually.
A common theme here, as everybody has who responded in this team, is data is king, and that is the foundational basis of what we're doing here. And as folks have questioned, there is biases to it. The data has to be accurate. It has to be evaluated periodically, and training on the folks who are actually taking that data in, because that is very foundational. So thanks for that response. Next question: bridge deck condition cannot improve without intervention. Did you model the intervention in the form of maintenance action in your predictive model? And I think you've answered this previously, but it's a slightly different question. That first question, bridge deck cannot improve without intervention. That is correct. Now, we have seen in some of our data where slight adjustment, 1 point up or down based on, again, the inspector's trained eye looking at it, or even what we've seen is a new inspector in that area comes in versus one that had retired and been there for 15 to 20 years. So a change of approach. Yeah, 1 point we could see, but we've also experienced where an increase or a decrease of 2 points without any kind of intervention. And especially most concerning is the one where it went up 2 points. So now, as far as modeling intervention in the form of maintenance action in your predictive model, I think that could be a possibility, but that just adds in some more complexity to your modeling. But certainly, the data set as far as not just the NBI, National Bridge Inspection, but you alluded to it, the efforts of maintenance, if that's captured or needs to be captured, that tells the complete story. Because yes, NBI is a snapshot in time that is taken for folks that don't know, right around March, and was submitted to FHWA. But in between the previous year, there's a whole lot of things happening, and that the condition ratings may change, the posting or non-posting of a bridge may change based on deterioration. But there are certain bridges that we look at and make sure that it is not closed for that long. So that there goes that policy as well of critical freight networks or evacuation routes that you will never see it fluctuate between the NBI data. But Dr. Mee's point, if you look at more of a dynamic set, that may tell a different story, and certainly a challenge to have a dynamic data set. So stating that the bridge condition will improve in the future without inclusion of data of how much funds will be spent in maintenance and other maintenance action may not be meaningful. Could you elaborate? How did you include this factor in your development of predictive models?
Short answer is we have not, and it's just that the data reflects all the actions. And it's our responsibility as we train the model, if certain variables are important, maintenance actions. If we have the solid data to correlate that with NBI data, because this data incorporates everything, funding level, inspectors, observation, and maintenance actions, and everything, pretty much we're training with it. And if the funding level or maintenance action could be a variable, if we have a good solid data, and also another thing is if we relate it, does it really relate well with the prediction? So there will be our future work, and it will be great that we can answer that question, and also particularly the scenario analysis that we're interested in developing as a part of next generation asset management, that would really help us as well. So yes, but we haven't tried.
And I will add in, at least for Georgia DOT, part of the process is that we're ongoing as we add into that selection process life cycle LLCA, life cycle cost analysis into the selection. So whether it's you go with a repair and rehab or replacement, that's starting to be part of our process. So probably a couple more questions here. Could the model be trained to recognize policy changes affecting ratings?
Absolutely. We just need to know what policy changes have been made as a variable, and I think finding the documentation of that, exact timing of that, I find it really challenging. But if those who ask the question have a good data showing the policy documentation and tell us which state DOT you're with, we'll be happy to try that as a variable.
I believe so, and I think that may be alluding to possibly on a national level, the SNIVI, the new specs for the inspections that are coming and being graduated into the whole process. But I will say, you are very much usually seeing our data. We do have that specific type of interesting policy change back in 28 that we're seeing the data having an effect on that. Maybe two more questions here. Could your model recommend evacuation areas and routes based on expected rain amounts in a dynamic mode?
Yes, certainly. I mean, that's our future goal. So one of the application I showed is we can apply it for flooding conditions, flood scenarios, and then it's again just like the prediction model. We just need to have enough database for any future evacuation scenarios, and then we can certainly do that. Apply it for our network model for that scenario.
At the core of that, we have a data governance. So that we identify the essential element that really goes back to if you can provide data and the governance structure as a part of ADA committee, I think we'll be more successful in predicting. I think we have the technologies and computer science sees our model to be pretty simple. We have a few variables.
I'll go with that's the last question. I will say again, thank you for all your hard work and ongoing work. And the one thing I will put forth for the folks as they leave this webinar is this is not the traditional skill set for a bridge designer, but it is a skill set that's evolving. And that's where, again, Dr. Mee brought it up, a workforce development scenario where we need to train our next generation folks as well coming into the pipeline to think not just about designing, but also managing and really dealing with large amount of data and how to correlate it. So that said, Freya, I'll hand it back to you.
Thank you again to today's presenters for sharing your IBT, ABC, UTC research work and for your thoughtful responses during the Q&A session. Thanks also to Don and Paul for moderating the Q&A session and to all of our participants for your interest, attendance, and questions. This concludes today's seminar. Thank you.